All right, let's talk about thin lenses. Thin lenses, you can find these suckers everywhere. All kinds of cool optics comes out of this. What is a thin lens in the first place? Well, thin lens is more or less defined as any lens whose overall thickness is relatively small compared to their eventual radius of curvature. Now, a thick lens could either be a converging or diverging lens, which basically means that when light travels through it, it's either going to bend it towards the principal axis or it's going to bend it away. And so, let's define those two. You've got your converging lens, and it's going to behave a lot like your converging mirrors, which were your concave mirrors, but it's not as easy to identify. The converging lens will always be thinner at your edges than it is in the center. I'm going to come back to that thought in a second. Your diverging lens is a lens that when light passes through it will actually diverge away from the principal axis, and again behaves a lot like your diverging mirrors, which are your convex mirrors. However, again, not as easy to identify. It is always going to be thicker at your edges than it is at your center. So in these two pictures on the left and the right, pretty easy to see. You see that it's thicker in the center for the lens on the left, which means it's converging, and it's thicker on the edges for the lens on the right, which means it's diverging. However, if you see some of these other lenses here in the middle, it's not as immediately obvious. For example, let's look at this converging meniscus. If you follow the rules, it's pretty straightforward. It's going to be thinner at the edge than it is in the center, so this must be converging. But if you try to remember what a converging lens looks like, this might not be what you pick because it doesn't quite look like what you might typically see drawn in a textbook or used in a lab. Same thing's true for your diverging, if not more so. Pretty straightforward with your double concave or your plano concave, which means one side is plane and the other side is concave. But look at this diverging meniscus. This is relatively hard to see, but it is indeed thicker on the edge than it is in the center, and so this will cause it to diverge. You might find many more extreme scenarios where it gets very difficult to determine just by looking at it. You really will have to compare the edges to the center. Alright, so let's break it down in terms of equations and sign convention. Make sure we're on the same page before we start getting into ray diagrams. Here we go. Here's the equation that you got to really know, or at least three equations. You've got your, your lens equation, the thin lens equation. 1 over DO plus 1 over DI equals 1 over F. And then you've got your magnification, which is the ratio of your image height to your object height, or your image distance to your object distance. We will still have to toss that negative sign in there because of the whole location of the image. Let's get into sign convention 2. Your focal length will always be positive if it's a converging lens, and it'll always be negative for a diverging lens. This is really important to pay attention to. This is where a lot of folks mix up their math because they forget this key tidbit. If F ends up being negative, you know you're dealing with a diverging lens. If you have a diverging lens, you better plug a negative number into this equation here when you're trying to calculate your other variables. Image distance will always be positive if the image is on the opposite side of the lens as the object. That'll be for all real images. Real images for a lens will always be located on the opposite side of the object, opposite side of the lens as the object. If the image is on the object side of the lens, or if it's a virtual image, it'll be a negative distance. Keep that in mind, because that almost will seem counterintuitive, because you have the object on one side, the image on the other side, which is a real image scenario. Both should be considered positive. Then, in the scenario where both are on the same side, the image must be considered negative. And we'll work through examples on that. And lastly, the height convention is still the same. If it's upright, the image will be positive, and if it's inverted, the image will be negative. Another term that's new for lens that you do need to know, the power of the lens, and that's going to be the inverse of its focal length. The power of the lens, using the term power should make sense. It's really the ability to bend those rays and focus sooner than other lenses. So for example, if I've got one lens that I'll quickly draw and the rays converge at a point pretty far away compared to a different lens that might converge sooner, like that green spot. Lovely drawing, I know. That green lens will be more powerful than the black lens because it's causing it to focus sooner, bend those rays easier, or more, I should say. And another term that's related to power is called dioptic value, which is more or less the unit of power for a lens. So one diopter is going to be equal to 1 meter to the -1 power because of that inverse bit. All right, how do we draw our principal rays for a lens? Well, your construction rays for a lens are eerily similar to your construction rays for a mirror. Because remember, you're going to have specific rays that will behave in specific scenarios that you can rely on every time. Well, let's just go through a quick example here. If I have an object just chilling here, you can tell, you know that, let's say the tip of that arrow, there are rays going in a multitude of locations, an infinite number of locations. But at least one of those rays will approach the lens parallel to the principal axis. At least one of those rays will pass through the focal point on the object's side of the lens. And at least one of those rays will pass straight through the center of the lens. Let me draw all three of them. Before I do that, let's talk about this focal point bit. Every lens will have 2 focal points. And for a thin lens, they're going to be equidistant on either side of the lens. It's helpful to draw a center line through your lens, even though that might not physically be there, to help you with your measurements. What we called the center of curvature for a mirror is not the center of curvature for a lens. This is really just 2F, and it's just a point there to help us with our geometry. The only physically important point is actually F. So again, we have an F and a 2F. You'll also find some folks toss a prime over on one side, and that's there to imply that's the image side. So if the object is over here, this will be F prime, and then the object side F will be F. I've even seen some folks flip that. Really, the prime is just to distinguish as the other F. Let's draw each of these. Like I said, there are more than these 3 rays, but these 3 are your helpful rays. So one ray will go parallel, and it's going to hit the lens. Now, in reality, it'll refract through this lens and then pop out through F. But when we go to draw these, because these are just some tools to help us figure out where the image is, you're encouraged to draw that parallel ray to the center line. And then when it gets to the center line, you're going to bend it. It's a converging lens. So it's going to go through F on the non-object side. So non-object side F. You'll have another ray that may go through the object side F. It will hit the lens. Again, it'll refract in this middle area. But again, you're just supposed to draw it to the center line. And it will refract so it comes out parallel to my principal axis. Just like with mirrors, your focal ray will be basically opposite of your parallel ray. And then lastly, you have one that'll go through the dead center of the lens. And you can think of this like the center of curvature ray for a mirror. But again, remember, for a lens, there really isn't an important value associated with center of curvature. In fact, the center of curvature is much further away than 2F. So we just say the dead center of the lens, and it literally goes straight through without any issues whatsoever. It won't refract whatsoever. This is the ray that just passes through and maintains orientation. All you need to draw are 2 of these rays, and once you know where those 2 rays cross, you know where the image will be found. So let's break it down into each individual case. And I want you to really think about your concave mirror cases and compare them to your converging lens cases. You're going to find out that they're very, very similar. And so this first one is that special case that a lot of folks don't even call case 1. It's kind of your pre-case case. And this is a scenario when the object is so far away that we're going to call it at a point of infinity. It's well beyond 2f. So far away such that every single ray that leaves it will travel to the lens parallel. So just as before, this is your special case that won't look like all your other cases. Every single ray that leaves this object will travel parallel, and every single ray will refract through non-object side f. And I can draw a ton of these rays if I wanted to, but every single one will end up converging to the same point, f. And so like I said, I can do this over and over and over again all day long, and every ray will pass through f, which does imply that this image will be found right there, right at the non-object side focal point. So, again, this is a special scenario. This is a situation in which we are going to get this kind of finite little tiny image right at the focal point. This is how we can measure the focal point of a lens. Take parallel rays, see where they converge. That is the focal point. Measure it with a ruler. We now know f for your particular lens. And I encourage you to get some lens and try this yourself. Any of you that have ever played with a magnifying glass in the middle of summer will have practice case 1, because this is where you're basically taking something really far away, the sun, and you're focusing it at a specific point, the focal point for that magnifying glass. So, this diagram, this little picture up here, that little spot where you're burning through the paper, fortunately you're not burning little things like ants, right? You're burning through paper or a twig or something. That distance right here, that is f. That's the distance of the focal point for that lens. Alright, so the image, well, you can't quite see it. We still need to identify everything. The image will be located at f. And you got to believe me, and I'll show it to you in the other cases. It will be reduced. I think you can believe me on that one. And it will be inverted. That's the part that you just have to trust me on right now. And because it's on the non-object side over here, it's real. Another way of remembering it's real is this is literally where the light is. The light will pass through that lens and continue. So we actually see it over here. Virtual images, we extrapolate the light rays back onto this side. And you'll see examples of that shortly. All right, let's go to case 2. Let's follow the pattern here. We're going to move that object closer to 2f, but it's at a finite distance. So we will have now the chance to draw more than one ray. And just as before with mirrors, what we need to do is identify at least 2 rays for one particular part of the object to know where that object is. So I'm going to take one ray and I'm going to have it travel towards that lens parallel to the lens. This is my parallel ray. Again, there's an infinite number of rays, but at least one will be parallel to the lens, and then it will refract through the focal point. At least one ray will pass through f until it hits the center line of the lens, and it'll refract parallel to the principal axis. I'm going to go ahead and draw the third one just to show it, but we don't need to because we've already drawn enough. But at least one ray will travel straight through the center of that lens without any sort of refraction at all. As long as 2 of the rays are intersecting, we now know the point of divergence. So if I had my eye here and I was looking at these rays, it'll appear that the light actually originated from that spot. And that's where we're going to see the image. So we now know enough information to know that's where the tip is. And just as before, if we begin on the principal axis, the base is at the principal axis, it's going to stay on the principal axis. So it helps make our lives a little simple by giving scenarios where it starts in the principal axis and finishes at that diverging spot. And I'm kind of messing around with my program here. It's taking a little bit for me to get that arrow drawn properly, but you get the idea. There it is, flipped upside down at that location. and it is, of course, relatively tiny. So let's identify what we know about this image. This image is, well, let's see. It looks like it's located somewhere between f and 2f. So it's going to be between f and 2f. It looks like it's been reduced in size. It certainly appears inverted to me. And as a result of it being inverted, it's definitely real. Not only is it inverted, or not only is it real because it's inverted, it's real because the light is actually there. This, believe it or not, is more or less how we see anything. Our eyes actually utilize this case. This is how we detect most images, because the object is a finite distance outside of 2f, and those rays will converge in the back of our eyeball. And we'll get into all that stuff at a different point in time, but get that. This is what's happening. All right, let's look at case 3. Or the situation in which we're now taking the object and we are going to place it at 2f. So again, pattern, really far away, image at f. Get closer to 2f, image between f and 2f. Get on f, or on 2f, where do you think the image will be? Think about the pattern. Where will it be? Let's figure it out. We're going to draw one ray parallel to the center line of the lens. It's going to then refract through f. Bam! Then we're going to take another ray, and we're going to, you know what, I'm going to do this one. I'm going to do the center one because that's the easiest one to draw, right? Take your ruler, line it up right through the gut, and there it goes. Try to do this one a little bit more carefully than I did, because this is one of those scenarios where if you do it correctly, it'll look correct. If you do it wrong, it'll look really wrong. And this is a scenario where I kind of did this wrong, or not completely wrong, but wrong enough, because if you follow the pattern properly, this image should have been located at 2f, and heck, it should have been the same size. Notice mine's a little bit off of 2f and a little bit bigger. Well, this is because my image itself was a little bit wider than my 2f dot, and my rays weren't exactly drawn properly. Try to take your time a little bit more than I am. I can fudge mine a little bit because, well, I have a computer program that allows me to do that. So I'm going to play with this a little bit so I can get my rays looking the way they're supposed to look. And I still don't think I'm going to get it done right, but I think you get the idea. And so, really, image should be located at 2f. Don't lose too much sleep over this. This is very similar to case 3 for your concave mirrors. Image, it is at 2f. It is same size. It is inverted, and it is indeed real. Okay, let's move on. Case 4. Well, where are we going to go for case 4? Infinity, finite, 2f. Yeah, probably between f or 2f. Let's go ahead and exaggerate this so it's not dead center. Let's move my way a little bit closer to f, just so we can understand that this exists anywhere between f and 2f. All right, so pattern. Let's see. Infinity was really, really tiny at f. At a finite distance, it was still tiny between f and 2f. When we placed the object at 2f, the image was the same size and was located at 2f. Now we're taking this object and placing it between f and 2f. I wonder where the image will be. Let's check it out. Ray comes into the center line. It will bend through f. Bam. Another ray comes in. And yeah, I'm going to go through the gut, right through the center. It's the easiest one to draw. Why not? And so I got to extend these arrows, these rays, until I actually see a point of convergence. And this one's going to be really far away, isn't it? This one's going to be gone. I might need to kind of fudge this a little bit to try to over-exaggerate what's happening here. I don't need to fudge it. I just need to play with my computer program. So let's try to move everything so we can see what's happening here. Magic. Man, don't you wish you can do this on paper? One day we'll be able to do that right on regular paper. We won't even need tablets. We'll be able to just magically move stuff around. Heck, maybe that day's even out. I just don't know. Wow, this is way out here, right? Okay, that's going to be enough for me. You guys are just going to have to imagine where it is. Nah, might as well keep inchworming. Sure enough, they will eventually intersect, I promise you. There they are. There it is. Good enough for me. Now I see this image. The tip of that object is way, 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 way out here. Remember, that baseline needs to be extended. So I got to take this guy and kind of make it go out here. And this arrow is going to be huge. It's going to be huge. All right, there it is. We've got, well, maybe right there. Yeah, it looks good. We've got a very magnified image, don't we? Interesting, isn't it? Image. Well, let's see. Image is way beyond 2f. It is enlarged. It is inverted. And remember, it's still going to be real. That light is still located on this side of the lens. Can you think of a scenario that utilizes this principle where you take a lens and you look at something tiny and you make it look bigger? I'm not going to quite tell you, but I know you've used it in other sciences before. All right, let's check out case 5. Case 5, all right, infinity, finite, 2f, in between f and 2f, there it is. We're going to place this object at f. And if you remember case 5 for the concave mirror, it was also a relatively special scenario. And it will indeed be a pretty special scenario here. We've got at least one ray that goes parallel, and then it converges through f. Bam! And then you've got another ray that, of course, will go right through the center. And if you take your time and you do this properly, you will notice, lo and behold, these rays are parallel to each other. Just as before, because these rays are parallel, you're never going to find a point of convergence or divergence. I mean, we can extend this back forever, and they will always stay parallel to each other. So, what do you think? Yep, no image. And another way of looking at this is, once again, this ends up being a beam of light. You can so totally take a flashlight, shine it through a lens like this, and you will get this nice beam of light going through. All right, let's roll on to case 6. Case 6 is indeed going to follow a similar pattern of all the rest. We're going to take that object, we're going to toss that inside of F, and we're going to see what happens. Now remember, case 6 for the concave mirror ended up being our one and only virtual image. I wonder if that's going to be the case here. Maybe. Let's see. Parallel ray hits that center line, and it will, yep, it'll go right through F. And then we've got another ray that's going to go right through that center of that lens. And I know I've got a pretty exaggerated lens here. But if my eyeball was over here trying to look at these rays, it's like, I don't know. They're not appearing to converge from the real side of this lens. So we're going to trace those rays backwards. And sure enough, yep, there it is. It appears that these rays appear to converge from the object side. Now understand, the rays are actually over here, but they appear to have come from back here. This is the virtual side. This is a virtual image. We know that's true because the rays converge at a point behind the object, or behind the object side, or on the object side, which is to say. Not only that, the image is showing up as, let me just duplicate that instead so I can compare the two. It's showing up as upright. And remember, upright images, they are virtual. And so this is a virtual image. So where is the image? Well, we're going to say on object side. Where in a mirror, we were able to say behind the mirror. But we're not going to say behind the lens in this case because light does exist on both sides. In this example, though, the image is on the object side. It is enlarged. It is upright. And it is virtual. Now, once again, let's think of another scenario where you take a lens and you place it over a really tiny object to then see that object as bigger. Again, not going to quite tell you. I want you to think this one through, but you've used this probably many times before. All right, let's get to our last scenario here, and that's for our diverging lens. Just like with a convex lens, there's only one scenario for a diverging lens. Every image will end up looking the same way, not the same way as in size and whatnot, but as in the same attributes, whether it's real or virtual, upright, inverted, things of that nature. So let's go ahead and try to figure that out. I'm just going to place this randomly anywhere. It doesn't matter. Also remember, because it's a diverging lens, the focal length is going to be considered negative when we go to do our math. Alright, so let's take our first construction ray. I'm going to go parallel to the lens view. I don't have a center line drawn, but yeah, it goes to the center line of that lens. And instead of it converging through F like all the other ones, it's actually going to diverge away. And where does it diverge from? Yeah, you probably are guessing it. It's going to diverge from object size F. So it's actually going to leave out like this. Now I need you to understand that although it looks like this light ray came from down here, I just have this portion drawn here to help guideline. It's more like a construction guide versus where the ray actually is. Now I don't want you to go and erase your paper or anything like that, but in reality this is what's happening. Parallel diverges outward. I'm going to keep this drawn here because I think it's important to keep it there so we understand when we're going to look back at this in the future that this ray originated from, or assumed it originated from object side F. I'm also going to draw my center ray. I'm going to do the ray that goes straight through the gut of this lens because it's going to help me because it's not going to refract. And so where the heck is that image? Well, it's actually done for you. Because this part was here, my eyes will trace these two rays back to where they appear to have converged from. So it's actually, bam, right here. Diverging lenses are easy. As long as you remember the rays diverge, you're not going to screw this up. So where's the image? Yep, the image is right there. What is true about the image? Yeah, it is virtual. So let's draw what we know, or write what we know. We know the image is, once again, we're not going to say behind the lens. We're going to say on object side. It is indeed reduced. It is upright. And it is virtual. So compare this to case 6 for your converging lens. The only difference here is the converging lens made it enlarged, and the diverging lens makes it smaller. That's going to come into play. It's very important to understand the difference. Those are really the only difference as to how the image appears. Of course, how you draw it is definitely different. Okay, that is it for lens. I hope you practice these. Try testing yourself out on your equations, the whole gambit. Thank you.